Hello, welcome to my talk on the simple Reynolds number and their significance in fluid mechanics. The definition of Reynolds number seems quite simple, but when we use it in practical problems in fluids, we might have the problems how we can choose the parameters for Reynolds number calculation. So the problems can be well presented use Reynolds number. As I have shown before in my talk on what is the physical meaning of Reynolds number, in physical understanding, the Reynolds number is an indicator of the ratio of fluid inertial force over the fluid viscous force. And I have also shown using the dimensional analysis, the fluid inertial force and the viscous force can be roughly presented use these expressions. Note here, these are not exact formulas for the forces, but they are very good indicators. For instance, if either the fluid speed u or the length L is doubled, while other parameters are kept same, the fluid inertial force would be nearly quadrupled, and the fluid viscous force would be doubled. In mathematics, Reynolds number is defined given as this. Here we can see ρ is the fluid density, mu is the fluid viscosity coefficient, and we can also use this nu, the fluid kinematic viscosity. In a strict definition, here in the definition of Reynolds number, u is called the characteristic velocity, and L is the characteristic length. What are they? Osborne Reynolds first ever carried out the systematic experiment study on the fluid transition from laminar to turbulent. He used 3 circular pipes of different size, and the experiments were under the different velocities, different viscosities, using different temperatures. And he found that his non-dimensional K number is a good indicator for the fluid state given as this. And now this number is named as Reynolds number. In this example, the characteristic length is the pipe diameter d, and the characteristic velocity is the mean velocity of the flow in the pipe u. So based on his experiment, he could show when the Reynolds number is less than 1900, the flow would be laminar, and when the Reynolds number is larger than 2000, the flow would be turbulent, and between is the flow transition from laminar to turbulent. In the modern fluid mechanics, the critical Reynolds number in the pipe flow would be 2300. That means when the Reynolds number is less than 2300, the flow would be laminar, and the pipe flow would be turbulent when Reynolds number is larger than 4000, and between the flow would be in transition from laminar to turbulent. So why we choose the mean velocity of the flow in the pipe as the characteristic velocity? If we look at the laminar flow and the turbulent flow, we can see in the laminar flow, the velocity would be well defined. But the turbulent flow, we can see the fluctuations of the flow. So the mean velocity for both laminar and turbulent flows are the well-defined velocity. However, if we consider the maximum velocity, in the laminar flow, it is a well-defined parameter. But in the turbulent flow, the maximum velocity would be very confusing. So that's why the general definition for the Reynolds number for the pipe flow is using the mean velocity of the flow in the pipe. In this slide, a famous flow, the uniform flow past the flat plate. Due to the fluid viscosity, there will be a boundary layer development as seen in this plot. For this example, we can define a local Reynolds number Rx as this. Here, nu is the fluid kinematic viscosity, and the characteristic length is the horizontal distance from the leading edge x, and the characteristic velocity is the velocity of free stream u infinite. So in this example, both characteristic length and velocity are well-defined parameters. And in this example, it's generally accepted when the local Reynolds number is less than 500,000. The boundary layer would be laminar, as seen here. In this case, the boundary layer thickness delta can be calculated using this formula. It's based on the horizontal distance x and the local Reynolds number Rx. So we see this is the plot for the laminar boundary layer, and the delta here is the thickness of the laminar boundary layer. And also, we can define an important thickness called displacement thickness, delta star, given by this, and it would be given by this. So compared to the boundary layer thickness, the displacement thickness in the laminar boundary layer would be about 34% of the boundary layer thickness. And we can also calculate the momentum thickness, theta, given by this expression. And we have the expression for the momentum thickness, theta. It is about 13% of the boundary layer thickness. So in the problem for the uniform flow past the flat plate, when the local Reynolds number Rx is larger than 500,000, the boundary layer would become turbulent. So in such a case, the Planck's 1/7 power law would be used for describing the turbulent boundary layer. If we look at the comparison of the Planck's 1/7 power law against the experiment data, we can see this expression would give a very good overall agreement with the experiment velocity profiles if the Reynolds number is not very large. Here, when the local Reynolds number Rx is less than 10 million. Based on this 1/7 power law, we can calculate the boundary layer thickness for the turbulent boundary layer given by this. Here we can see the boundary layer thickness is proportional to the local Reynolds number power of minus 1/5 rather than the Reynolds number power of minus half. This means the turbulent boundary layer thickness would be much larger than the laminar boundary layer. And accordingly, we can calculate the displacement thickness, delta star, given by this, and the momentum thickness, theta, at this. And here we can also calculate the shear stress on the boundary, tau w, given by this expression. And from this expression, we can also calculate the fraction velocity u tau, given by this definition. Here in this slide, we'll look at the Reynolds number for the flow past a 2D airfoil. In this case, the Reynolds number is well defined as this, with the characteristic length being the airfoil chord c, and the characteristic velocity would be the velocity of the free stream u infinite. So here we can see the characteristic velocity is a well-defined parameter. But for the characteristic length, why the airfoil chord c is chosen is because c is the most important parameter. And if we look at the problem, how the Reynolds number will have the influence on the airfoil performance, this is the example for the lift coefficient in different Reynolds number. So we can see when the angle of attack is small, the Reynolds number has no influence on the lift coefficient. However, when the angle is larger than 10 degrees, we can see the difference with the different Reynolds number. And the larger the Reynolds number, the higher the maximum lift coefficient. And the more significant influence of the Reynolds number is on the drag coefficient. See this plot. Here we can see a higher Reynolds number means a smaller drag coefficient. See the red line. And if we take the lift coefficient CL 1.2 as the reference, then we can calculate the ratio of the lift over the drag. For the Reynolds number at 9 million, the ratio would be 105. For the larger Reynolds number at 20 million, the ratio would become 130. This is an increment of 23.8%. In here, we look at the Reynolds number for the flow past the cylinder or a sphere and examine how the Reynolds number will have influence on the drag on the cylinder. The Reynolds number would be defined as this. Here, the characteristic length is the cylinder or the sphere diameter d, and the characteristic velocity would be the velocity of the free stream u infinite. In many reference books, we can see the drawing like this for the drag coefficient CD against the Reynolds number for the sphere and the cylinder. So we can see the drag coefficient for the cylinder is much larger than the drag coefficient on the sphere. And the trends of the drag coefficient with the Reynolds number are very similar for both sphere and the cylinder. And we see when the Reynolds number is smaller than 200,000, the drag coefficient would not change very much. However, at the Reynolds number of about 200,000, we can see the big drop of the drag coefficient for both cylinder and the sphere here. Next, we will have a look why the drag coefficient for the cylinder is much larger than the drag coefficient on the sphere. In an extreme case, when the Reynolds number is infinite, that means the fluid viscosity is zero. It would correspond to a potential flow. And there is an analytic solution for the potential flow past the cylinder. the pressure coefficient would be given by this formula. And similarly, for the potential flow past the sphere, the pressure coefficient would be given by this formula. And theta is the angle defined in here. If we draw out the pressure coefficient of the potential flows, we can see the green line is the pressure coefficient for the flow past the sphere, and the black line is the pressure coefficient for the potential flow past the cylinder. However, in reality, the flow is viscous, so the dashed red line are the pressure coefficient from the measurement for the real flow at different Reynolds number. The lower Reynolds number is 186,000, this line, and roughly happened here. And the second Reynolds number is 670,000, so it happened somewhere here. So we can see when the Reynolds number is larger, the pressure coefficient would be closer to the pressure coefficient of the potential flow. So we can imagine if the real flow passes the sphere, the pressure coefficient must be smaller than this green line. So that's why the drag coefficient for the sphere is smaller than the cylinder. In this slide, we will look at the Reynolds number for a ship traveling on seas. The Reynolds number is defined as this. Here, the characteristic length is defined as the waterline length L, WL, and the characteristic velocity is the ship velocity U0. Why we have to choose the ship length as the characteristic length rather than the breeze or the draft of the ship? It is because for the resistance of the ship length would be the most important parameter. The Reynolds number is especially important in studying the fluid resistance. For instance, ITDC, International Towing Tank Conference, recommended a formula for the ship resistance coefficient CF in 1957. It was based on Reynolds given in this formula. Another example is again from the ITDC recommendation in 2017. This is for the ship model experiment, and we can see for different model lengths the Reynolds number against the flow number. We might have nominal flow, transition flow, or turbulent flow. From this drawing, we can see if the length of the model is less than 2 meters, it would be very difficult to have the model test in turbulent flows, and the modeling on such a model would be not correct, since for the real flow around the ship is turbulent, but the model flow is the transition flow or the nominal flow, so the modeling is not correct. So we can see here the Reynolds number is very important for the model testing. If we need to decide what the size of the model is good for the model test,